Welcome to this course on mistake proofing using the powerful zero quality control system created by Dr. Shingo. As you may or may not know already, Lean Strategies International LLC's vision is to educate, empower, and transform organizations and lives around the world through the power of continuous improvement strategies. To do this, we work to provide affordable and comprehensive coaching, educational opportunities, and supplies that can be measured through the success and experiences of our partners and students. The method we will learn about in this course is based on the Zero Quality Control System. This powerful system will make your workplace and you more productive and efficient. In addition, the work you do will become much easier. The Zero Quality Control System breaks down the common ways that human mistakes occur and helps you learn to prevent them from turning into defects. This course will give you a comprehensive understanding of each of the steps in the system and will challenge you to go and use them. Throughout the course, you will learn about the Zero Quality Control System, Poka-yoke systems, tools that will help you prevent errors, and we will look at examples of how Poka-yoke works today. We'll also discuss a process that will allow operators and office personnel to apply the system and prevent mistakes in their everyday work. Like many courses with Lean Strategies International LLC, you will learn in comprehensive lectures, study handouts, test your knowledge with quizzes, and complete activities all throughout the course. You'll also have access to course materials anytime you want, so you can log in and work at your own pace. Rest assured, by the end of this course, you will have a much deeper understanding of how you can mistake-proof in different environments. So, look through the various descriptions, watch the free previews, and then enroll in the mistake-proofing course with Lean Strategies International LLC. And let's get started creating solutions that ignite your power today. Imagine a world where quality control doesn't exist. You either have perfect quality and don't need it, or you have no quality and desperately need it. Typically, the latter is more common. Zero quality control is an approach for achieving zero defects in an organization. Zero gives reference to the objective of the ZQC system, which is to produce all products and services with zero defects. The approach was first outlined in the book Zero Quality Control, Source Inspection, and the Poka-yoke System, which outline the main concepts of the ZQC system. The ZQC system is unique in the sense that it did not look to blame people for errors or human mistakes. Rather, the focus was on controlling processes in such a way that the process would not produce defects even if human error was introduced into the process. Dr. Shingo recognized that for the system to prevent errors, it needed to acknowledge that all machines and people will at times make mistakes. With that said, it is important to understand that mistakes can occur, and those mistakes do not have to result in defective parts or even defects. Therein lies the foundational secret of the zero quality control system: mistake proofing. Essentially, the system prevents errors, mistakes, and defects from occurring, which ultimately accomplishes the goal of the system: zero defects. Okay, before we go, I'd like to invite you to consider the following question, and if you are answering this question in our mistake proofing course, Please feel free to look through your handouts and review the lecture if you would like to before answering. If not, then ponder this question and consider writing down, commenting, or sharing your answer. How would your life or
Hmm.
place of work be
Hmm.
different if you achieved
Hmm.
0 defects? We'll see you in the next lecture. Let's imagine for a moment that you walk into your favorite store. There it is, the dream product that you've always wanted. Immediately, you begin picking up overtime, cutting costs, and when you have time, dreaming about your new toy. After a few months, you finally have enough. Excited, you run down to the store and grab the box off the shelf. For a moment, you think, maybe I should save a little bit of this money. But that's only a moment. You buy it, run back home to unbox and set up your new dream toy. You turn it on, and nothing. It doesn't function. Crushed, you return to the store where the owner informs you the product is back ordered and you will have to wait a few months to get a replacement. Why would you want 0 defects? That's exactly why. Defective products and defects not only impact a business internally, they impact the satisfaction of customers as well. This can result in lost sales, bad reviews, and possibly a product or service that cannot be sold. Many people wonder, is 0 defects even achievable? With so much of a 0 defect philosophy riding on and changing culture, it can be difficult to see anything other than failure. However, there is much more than that. In addition to improved customer satisfaction and loyal customers, working to achieve 0 defects will drastically reduce the costs, improve efficiency, and establish a foundation for problem solving. Formally defined, a defect is any output from a service or a product that does not meet the customer required specifications, standards, or requirements. Though a defect is not the same as defective, they both yield significant costs. For example, when a defect occurs, time, materials, money, and other resources have been invested already. If the part or information is deemed defective, it is all lost. With that being said, even a defect will cost you money in the form of rework, lost time, and possibly an output that you can do nothing with. Defects also slow a process down. They cause information and products to be reworked, and they often result in bottlenecks or lines that are stopped. On the other hand, when defects do not occur, a process moves more efficiently. When a process results in a defect, the primary objective would be to stop and work through the various levels of causation and discover why the defect occurred. As this problem solving process occurs, a foundation for problem solving and improvement minded people are developed. This is one of the most powerful aspects of the ZQC system, its focus on the process and not on people. As noted earlier, the system recognizes that people are not perfect and that errors will occur. This mindset creates an environment where problems can be brought forward and solved. In addition to this, the system gives people tools that they can use to prevent mistakes from ever turning into defects and solve problems one after another. As you can see, there are many reasons why 0 defects would be your focus. From the days of Shigeo Shingo and Philip Crosby right up until today, 0 defects is a recipe to lower inventory, improve efficiency, and reduce costs in an organization. Let's now begin looking into this powerful ZQC system and learn how we can begin moving towards zero defects. Nobody wakes up in the morning and thinks to themselves, "Today I think I'll destroy all the materials, products, machines, and information at the place of my work. Yes, that's what I will do. Try to create as many defects as possible." But sometimes, as humans, we make honest mistakes. When these mistakes result in defects, it is important to first allow the problem to be brought forward and reassure the individual that even though the problem has occurred, there is also an opportunity to get better. In the case of a defect, there are some general areas where defects occur, which we will introduce here. Starting with standards, procedures, and processes. First and foremost, we want to look at the process, the standards, and the procedures. When procedures or standards are not established, lots of guesswork can occur. This oftentimes is a key factor in the creation of a defect. If by chance standards and procedures are established and defects are still being created, the standard or the procedure may not be correct. Here's an example. If you're producing a batch of cakes and the process has the wrong ingredients tied to it, every cake will be wrong. The standards, procedures, and processes must all work in unison and appropriately. If they do not, you can be sure a defect will occur. Next is the stability of your process. Variability is real. When your process, machine, or materials have variability in them, you will not be able to produce a consistent output. This will result in defects and is a foundational concept in Six Sigma. For example, a process that has no standard will be performed differently each time, which means it will not produce the same result. A machine that does not run as tight as it should will produce defects from time to time. Likewise, if the materials or information you are using are not consistent, defects will occur. Next, we will look at the effects of maintenance. Another common cause of defects in both parts and information are worn down or not up to par systems. For example, if a computer needs maintenance or is not working properly, it may produce outputs that are defects. A machine that produces parts and has worn down tooling or mechanical parts may also create an environment that creates defects. Next, we will look at mistakes or errors. The final common cause of defects in materials or information is human mistakes or errors. In the book, Zero Quality Control, Source Inspection, and the Poka-Yoke System, we learn that even when all mechanical aspects and processes are functioning properly, human mistakes and errors can still occur. This could be forgetfulness, misunderstanding, misidentification, lack of experience, neglect, by surprise, or any other reason. Whatever the reason, mistakes do sometimes result in defects. Unlike the other reasons that defects occur, mistakes are oftentimes unpredictable. So, how do we catch these unpredictable errors? The ZQC system attempts to catch these errors with a control function before they turn to defects. Control functions work by creating an environment or conditions where everything that is needed to create the proper product or information is present. Remember, there are many different ways in which a defect can occur. These 4 common causes lay out a framework that defects can trace back to. However, you may consider making a list of things that cause defects in your process, at your work, or even in your personal life. Try setting a timer for 5 minutes and write down the different things that cause defects to happen around you. As you do this, you may find one example you would like to work on. If you're taking the mistake proofing course, you can answer the questions inside the course. If not, you may consider jotting your thoughts down on paper before moving on to the next section. We've all heard of the traditional process for quality improvements: plan, do, and check. This process is largely based on the check or inspection catching defects. However, catching defects implies the defects have already occurred. While it's certainly better to catch a defect in inspection, it would be much better to control the process in such a way so the defect did not occur. To do this, we need to understand a little more. Traditionally, a process, materials, machines, and information are planned. On paper, the plan looks great. Then the do happens. After the output is produced, inspection jumps in and checks the part. The part either passes inspection or it doesn't. When a part or piece of information does not pass the inspection phase of a process, it is typically rejected as something that does not meet the requirements. The information from the rejection is then passed on to someone for feedback and eventually some form of corrective action, improvement, or root cause analysis. This sounds great, right? In many aspects, yes. Defects should never escape. The downfall in this traditional scenario is that the defect still occurred. And while you may catch and stop a million feedbacks, you are catching them after the fact, not preventing them. Dr. Shingo reminds us in his book, Zero Quality Control, Source Inspection, and the Poka-yoke System, that an error is not a defect. Rather, the error causes the defect. With this powerful reminder, it is much easier to understand that we do not want to discover defects after they happen. We want to catch the error before it turns into a defect. In the ZQC system, this is done by creating an environment where the do and check occur at the same time. This helps ensure that the plan is executed the way it is intended, and if the plan is not correct, it is found right away. Essentially, the traditional method of quality changes from plan, do, then check to plan, do, and check. This scenario performs inspection right at the point or place where an error or problem could occur. This gives frontline employees who are doing the work an opportunity to detect and correct the error before their work is done. ZQC refers to this as source inspection, or inspection that occurs at the source. When the inspection occurs right at the source, the feedback is instant, and any problem that may have occurred can be corrected before the defect occurs. The Zero Quality Control system works best with implementation of 4 foundational elements that we will introduce here: source inspection, 100% inspection, short feedback loops, and Poka-yoke or mistake proofing. These 4 foundational elements have been proven to effectively help move from a process of inspection to an environment of a process control. We will discuss more in the coming modules. No organization will ever operate day in and day out with absolutely no errors. In fact, no person will ever live with zero errors. It is natural for us as humans to make errors and to make mistakes. This is why it is absolutely essential to the culture of an organization and to an individual that they understand errors are not the issue. It is when errors turn into defects that a real problem begins to exist. ZQC is different from the traditional quality improvement cycle in the sense that the do and check stages of plan, do, check are combined. This gives operators the ability to do and check at the same time, which ultimately prevents errors from transforming into defects. So, how does it do this? The Zero Quality Control System uses 4 techniques to combine the do and check phases. We will introduce those 4 techniques in this module and look at the specifics of each of the 4 techniques later on. Those 4 techniques are source inspection, or inspection at the source. This allows operators to inspect materials and information at the gemba or where the work is performed. Instead of inspecting only sample lots, all parts are inspected. This is known as 100% inspection. Immediate feedback. The ZQC system attempts to provide feedback instantly. This essentially means that if there is an error, the correction can occur right away. The ZQC system also integrates mistake proofing or poka-yoke. These devices check products and information. This is also known as error proofing. While all 3 of these elements are critical pieces of the ZQC system, the first is arguably the most critical. Oftentimes, problems are evaluated away from the source. This can lead your problem solving down paths that may not be in the right direction. Dealing with the problem at the source gives you access to more information at the source. This will allow you to see what is actually going on. Let's look at each of these 4 elements a little closer in the following lectures. A quick Google of the word inspection, and we find that it is defined in one way as careful examination or scrutiny. In chapters 4 and 5 of the book Zero Quality Control, Source Inspection and the Poka-yoke System, Shingo describes 3 different types of inspection: judgment inspections, informative inspections, and the method used in the ZQC system, source inspections. Judgment inspections compare products and information to a standard. If the product or information conforms to the standard, it is good. If it does not, it is bad. Judgment inspections are a great way to catch inspections before products and information leave a facility to go to a customer. Essentially, judgment inspections separate good parts from bad parts based on specific criteria. So, what's the issue? Because standards are generally written for complete products and information or at specific stages of production, the inspection usually does not occur until the parts or information are complete. This means that if there is a defect found, it is likely that it occurred upstream in the process, and not only is there no way of preventing it, you may never discover the information you need to identify where the actual issue occurred. Judgment inspections are considered to be a traditional inspection. Informative inspections are a bit different than traditional judgment inspection. Still considered to be part of the traditional inspection group, there are 3 types of inspections that Dr. Shingo outlines: statistical quality control, successive check of each product, and self-check of each product. Statistical quality control uses various statistical techniques to determine whether or not the materials or information being produced are acceptable. SQC does this by checking sample lot sizes after they are done processing. While this may provide feedback a little quicker than judgment inspection, it only checks a sample of what is being produced. With that being said, it does not ensure that 100% of processing is good. Another traditional form of informative inspection is successive checks. Successive checks are a form of inspection which allow people in the process downstream to inspect a unit or information that has been moved on to them from somebody upstream. This gives people all throughout the value stream the ability to catch defects and provide feedback. Like SQC, successive checks do not prevent defects, they catch them and provide information about the defect. The final form of informative inspection is the self-check of materials and/or information. Self-checks give people the opportunity to check or inspect their own work. This allows them to catch defects immediately before passing items downstream. With that being said, self-checks will give the operator feedback immediately if a defect were to occur. However, like the other forms of inspection, self-checks do not prevent defects from occurring, nor do they prevent natural human mistakes from happening. Of the three informative inspection methods, self-check of each product provides the quickest flow of feedback and information. The one major discrepancy with the self-check method is that as humans, we are bound to miss some of our own mistakes. As you can see, all three forms of informative inspection are indeed superior to the traditional judgment inspection. Informative provides feedback and collects information that can later be used to improve the process. However, it should be noted that all three forms of informative inspection catches the defect and does not prevent the defect. Preventing the defect from ever occurring is the goal, and this can only occur using source inspection. Source inspection inspects products and information at the source. This is quite different from the judgment inspection and informative inspection methods. Dr. Shingo teaches in his book Zero Quality Control, Source Inspection and the Poka-yoke System that source inspection accomplishes two critical components in any effort to achieve zero defects. It catches errors, and it provides feedback regarding those errors. These two components are critical in achieving zero defects as they give you the ability to catch errors before they turn to defects. Source inspection works in different ways to integrate the check and do stages of the traditional inspection model. It does this by using different methods to control the do phase. For example, when you enter information into a form and submit it, if you do not enter a piece of required information, the form will not allow you to submit the information. In addition, the form will oftentimes scroll to or tell you what you need to do to successfully complete the process. This do phase is stopped and provides information and guidelines at the source to successfully complete the form. In addition, you will notice that the form cannot be processed or submitted until it has all the required information and is done correctly. Another way that source inspection may work is by stopping a machine or line when a part is not set correctly. It may also trigger a warning light if a machine is not running correctly, or send a message to the operator when something is not working correctly. Source inspection is very effective when combined with the other three elements of the ZQC system: 100% inspection, short feedback loops, and quicker action. In addition, Poka-yoke. We will look at these three elements in the following lectures. If you had time, money, and other resources invested in making something, wouldn't you want to ensure that 100% of your investment was good? 100% inspection is just that, the act of checking or inspecting every single physical product or piece of information. Statistical quality control uses different sampling methods which do not ensure that everything being processed is good and does not ensure that the defect is prevented. Most organizations use SQC because they think that it may take too long to perform 100% inspection. With sensors and other techniques, though, this hurdle has long since been overcome. With the goal of zero defects in mind, this is important. Statistics in the form of control charts can show us whether or not a process is under control and do help identify processes that have variation in the output, but 100% inspection performed at the source maintains control of the process and prevents defects. It can even help catch an error and correct it before the error turns into a defect. 100% inspection also improves the feedback loop. Let's look at an example. Bottles are flowing down a line. They all complete the process and are inspected after the fact. Some of the bottles are found to be defective. Where in the process did the defect occur? That's a good question. A great deal of research and root cause analysis would need to be done to find the error back upstream. However, if the process was using 100% inspection, each bottle would be inspected right on the line. If a defect was found in the line, a warning light may pop up, or a marker on the bottle with a defect may occur to prompt a worker to go and dig into the problem. You could also use a control poka-yoke. If a bottle was found with a defect, this may trigger a stop on the line to bring the process into a more controlled review. Then the operator could look at the different aspects of the defect and conduct root cause analysis right at the point where the defect occurred and right on the bottle that had the defect. This would allow the operator to bring the process back into control. He could also correct the defect or the error that occurred. Now that we understand 100% inspection a little better, I'd like to invite you to ponder the following question. What challenges would I have to overcome to make 100% inspection happen today? If you want, you can write your answers on a piece of paper or share your thoughts with us in the course question or the comments section. You never know, maybe someone else has the same challenge that you have and could help them overcome with a little discussion. We'll see you in the next lecture. What does the word immediate mean to you? What does the word feedback mean to you? In the traditional informative and judgment-based inspection methods, feedback is delayed at best. In many cases during judgment inspection, the feedback never occurs. Not only does this make it difficult for errors to be prevented, it also makes it difficult to correctly identify problems. The quicker the feedback, the quicker the solution. In the case of the ZQC system, immediate feedback can often be achieved at the point of error or even before. How does it do this, you ask? The ZQC system uses different methods or systems that signal the users when a mistake or error occurs. This provides them with immediate feedback. In many cases, the signal can occur before the item is actually processed. In our example of a website form, the information cannot be submitted unless all required items are complete. This immediate feedback occurs before a defect can. Another example might be an electrical plug with 3 prongs. If you try to put the outlet in upside down, it will not work. This is immediate feedback that you need to flip the plug over to proceed. That's immediate feedback. In the next lecture, we will look at one of the most powerful and well-known pieces of the ZQC puzzle, poka-yoke. Before you go though, take a minute to ponder this question. What errors or mistakes have I witnessed that, if found quicker, could prevent a defect? Feel free to share your thoughts, and we'll see you in the next lecture. Errors, mistakes, and accidents all can quickly turn to defects. As we've learned, the ZQC system, developed by Shingo and shared in the book Zero Quality Control, Source Inspection, and the poka-yoke system, uses 4 different elements to achieve its goal of 0 defects. The 4th element is one of the most popular in continuous improvement, poka-yoke. Poka-yoke is a Japanese term that means mistake proofing. Poka-yoke devices essentially help facilitate 2 very critical aspects in preventing errors. They help accomplish 100% inspection. They also provide quick and almost immediate feedback when errors do occur that helps an operator take corrective action before the error turns into a defect. In the simplest form, a poka-yoke will either shut down a process, machine, or line when an error occurs, or signal the operator. The most effective poka-yokes are achieved with source inspection. However, poka-yokes can also be effective with informative inspection methods. Keep in mind that the informative type poka-yoke checks only after the defect or error has occurred with either the successive check or self-check methods described earlier. While this is effective in stopping the defects from traveling, it is not as effective as a poka-yoke at the source. Now that you understand what a poka-yoke is and the basics of how they work, we're ready to discuss the how of poka-yoke and begin preparing you to implement poka-yokes on your own. In the coming lectures, we will look at how poka-yoke works, the different types of poka-yoke, various sensing devices, and we will challenge you with a few reflective questions. With that being said, we'll see you in the next lecture. Mistake proofing. That sounds like a dream, doesn't it? Who wouldn't want to have 0 errors, 0 mistakes, and 0 defects? How is this accomplished? In part, it is through the poka-yoke method that helps to control the production process of information and products when applied. It does this 2 different ways. The first is a control system or prevention system. The control system stops a process when something occurs that is out of compliance and does not let the process move forward. The warning system or detection system does not stop the process, rather it makes the operator aware of an issue and prompts them to stop the machine or deal with whatever issue may have triggered the warning. Wherever possible, a control system should be used. This is because the control system does not depend on a person. It stops the process based on any abnormality. With that being said, if you cannot use a control method, you should use a warning system. There are many different types of systems for both control and warning. Some use lights, others have sounds, and many use other forms of sensory notification. Both types will make people aware of an abnormality, but only one type will stop or control the process automatically. The key difference between the two is that one is automated and the other is not. Poka-yoke also uses 3 different methods to facilitate the control or warning of an error. Those 3 methods are contact methods, fixed value methods, and motion step methods. Each of these methods are very effective in detecting abnormalities. We will look at each of the methods individually in upcoming lectures. One of the ways the Poka-yoke system can control or detect errors is by making contact with abnormalities. Contact methods work based on contact. In other words, if a product physically contacts something, this should trigger a device to stop or not. Ultimately, the contact method uses some type of sensing device to identify defects in a part's shape, color, size, or other physical attribute. For example, many cars will beep when they are backing up. If the car gets too close, some cars will automatically stop. Other contact methods work based on energy. These energy-based contact methods sense when something is not correct. In the same example of a car, vehicles will oftentimes increase the rate of the beeping when it gets closer to hitting something. Contact methods may also identify errors or defects using a shape, size, color, or other physical attribute. Limit switches and proximity sensors are oftentimes used to gauge how close or far something is from making contact and ultimately preventing an error from occurring. For example, if we want to avoid placing an item incorrectly, we may have an asymmetrical design that allows the part to fit only in the correct orientation. If the item does not fit, it will make contact and prevent the item from going in. The contact method is one of the most frequently used methods in Poka-yoke. In the next few lectures, we will look at other types of Poka-yoke methods that you may consider using. We'll see you in the next lecture. Fixed value methods, also known as constant value methods, is a technique that can be used to both control and warn a person when the process is not in compliance or an error has been made. Fixed value methods can be used in a variety of different ways. This method should be used when a fixed number of parts or information needs to be entered or attached to a product. It can also be used when a fixed number of operations needs to be done at a workstation. When using the fixed method, a device counts the number of times something is done and signals or releases the product when the value is reached. The basic idea is that if you have a fixed number of steps, operations, or actions that must occur in a process and it needs to be done, it can be counted. When the process does not reach the required number, the process will either trigger a warning and tell the operator what to do, or trigger a control and stop the process altogether. The fixed method can also be used with the number of items. For example, if you were building a piece of furniture that you purchased, your instructions may include a bill of materials. Let's say that one in particular was for screws, and your instructions called for 10 screws, or the exact number needed. Let's say you then put your furniture together, and at the end of the process, 1 screw was remaining. Because there is a fixed value on the number of screws, you would know that 1 screw was missing. Fixed value methods often use counters, limit switches, or some other means of tracking the fixed value. Some different ways that a fixed value is performed is counting or measuring the number in advance, using a bill of materials, or establishing an obvious standard. If you have a quantitative number that can be tracked and used to prevent errors, you'll want to look into the fixed value method. Now, let's look at one more method of implementing Poka-yoke. See you in the next lecture. Errors can occur when a step in a process is skipped. Sometimes those errors will turn into defects. In the motion step method or sequence method, the focus is on ensuring the process steps are followed before starting the next stage. Not allowing the mistake to be made in the first place is a great place to start. The motion step method essentially determines whether the necessary steps in the process have been followed. Color coding, labeling, tagging, and other forms of visual management are common motion step methods and used all the time in Poka-yokes. These are inspected to ensure the prior steps were performed before the current step can begin. This oftentimes includes sensing or tracking motions or steps that may occur in the process. For example, if a process step has established a cycle time and the step is not executed in the appropriate cycle time, this may cause the machine to send a warning or even a control in the form of a process stop. The motion step method oftentimes uses sensors and other devices to track and count steps as they occur. If the step or movement does not occur when it should, or occurs after or before the appropriate time, the sensors will trigger the equipment to send a warning and may stop the machine to regain control of the process. In other circumstances, a process may be established with items that are laid out in a sequence. This helps the operator fill out the appropriate information in the correct sequence or select the appropriate items at the appropriate time. Keep in mind that the heart of Poka-yoke is error proofing. We've outlined the contact method, fixed value method, and the motion step method. But, like any continuous improvement tool, you may discover other methods as well. As long as you improve and prevent errors and defects, those methods should be used too. We'll see you in the next lecture. The three most well-known methods used in Poka-yoke are the contact method, fixed value method, and the motion step or sequence method. Each of these three methods can be used to warn an operator or to control a process. In addition, they can be used at the source for inspection or in the informative inspection format. But how do these different methods sense that an error may occur? How do they sense that something is not right or that an abnormal condition is about to occur? Typically, anyone trying to mistake-proof a process, especially if they are following Dr. Shingo's suggestions in the book Zero Quality Control, Source Inspection, and the Poka-yoke Method, will use one of three types of sensing devices: physical contact sensing devices, energy sensing devices, and physical condition change sensors. Physical contact sensing devices are one form or method that can be used to sense when a process may have an abnormal condition. These devices work by touching the product, machine, or object physically. Examples may be a limit switch, These can verify the position of an item or identify whether an object is there or not. When this occurs, the limit switch may trigger a warning to the operator or control the process by shutting the machine, line, or process down. Energy sensing devices work in a similar way to physical contact. The difference is they sense energy rather than physical contact. Some examples of energy sensing devices are vibration-based sensors, photoelectric switches, proximity switches, area sensors, displacement sensors, tap sensors, beam sensors. Energy sensors use forms of energy, such as photoelectric switches, which use beams of light to measure items that are transparent. Some backup cameras also use sensors to gauge the distance that is left before an object is hit. There is one other type of sensing device that contains three subcategories. It is called condition or conditional change sensing devices. These devices are broken down into three categories that contain pressure sensing devices, temperature sensing devices, and electrical current sensing devices. Pressure sensing devices look for changes in pressure or errors in pressure. For example, if an air compressor needs a certain amount of pressure to operate correctly, the device would monitor this and warn a user or shut the machine down if an error occurs. Thermometers, thermostats, and temperature gauges are different tools that can be used to sense temperature changes. Some examples of different processes where you might want to use a temperature sensing device may be preheating an oven, warming up injection molding machines, preheating dies, and freezers that need to maintain a specific temperature. Like other forms of poka-yoke, if the device finds that the temperature is not correct, it may warn the user with a signal or automatically adjust the temperature by turning it up, down, or even shutting it off. The final type of sensing device is a device that senses when a specific electrical current is altered or changes. Like other devices, it attempts to identify a current that is abnormal. This can be used in electrical currents, welding, and wiring of items. Whether the device is a pressure sensing device, a temperature sensing device, or electrical current sensing device, ultimately the device must get the attention of an operator to correct the abnormality. It needs to be able to control the process itself. For example, many facilities use on-on lights to notify operators when a machine is running correctly and when a problem occurs. The on-on changes the visual based on the status of the machine and provides a way to identify normal and abnormal conditions. While visuals are a great way to get the attention of operators, other sensory devices may be better. For example, if an error, mistake, or defect occurred, would a loud noise get your attention quicker or a light? In most cases, a loud noise would get your attention quicker than a light. With that being said, you will need to decide what devices are appropriate to get the attention of workers or ensure that the poka-yoke can control the process on its own. But these are different devices that help us reveal abnormalities and grab the attention of operators. With that being said, it's time for you to go implement some devices of your own. We'll see you in the next lecture. There are many examples of poka-yoke and mistake proofing that help us avoid defects. Poka-yoke is found in manufacturing, service, and information systems. They can also be found in everyday life. In this module, we will look at some examples of poka-yoke that you may not have noticed before. Keep in mind that any form of error proofing should be inexpensive, if not free, and as simple as possible. Also, Recall that there are different types of inspection. We have judgment inspection, informative inspection, and source inspection. In most cases, and if possible, you want to shoot for source inspection. But if source inspection is not a possibility, or you cannot think of a way to move your poka yoke to the source, then begin with informative inspection methods. We will look at examples of poka yoke for source inspections. Remember that any form of poka yoke is going to be specific to your process, so involve people from the front lines, or the gemba as we say in Lean, and allow them to come up with innovative solutions. These examples may help spark ideas or generate thoughts, but may not work in your situation. As a reminder, poka yokes that occur at the source is a device or method that prevents an error during the process. There are two ways for this to occur: control or warning. Let's look at an everyday example. You may not realize it, but a microwave is a great example of a poka yoke at the source. The microwave will not turn on unless the door is completely closed and the start button is pushed. It could be very dangerous if a start button was pushed and the door was still open. This type of poka yoke is known as a control poka yoke, located at the source. Another example of a poka yoke at the source is spell check. Spell check works by linking to a dictionary of words, definitions, and their proper usage. When you spell a word incorrectly, for example in Google Docs, the word is highlighted. This is a warning poka yoke at the source. The user can then go back and choose to correct the word or not. You can also set your spell check to automatically change if you want it to. This prevents the document from being turned in with a misspelling and transforming your error into a defect. With these examples in mind, let's look at one example of our three different methods: the contact method, fixed value method, and the motion step method, which are all used as poka yokes. We will see you in the next lecture. Let's imagine for a second that you stamp parts on a die. There are only two directions the die could go in the die, but it is not uncommon for a piece to be put in wrong. You recognize this struggle, and in an effort to prevent the pieces from being stamped incorrectly, you build a poka yoke into your die. The die can now only fit the part in one direction, because if you try to place it in another direction, it will not make contact the correct way and cannot be put in the die. Another very common example shared in Dr. Shingo's book, Zero Quality Control, Source Inspection and the Poka Yoke Method, is an example of milled and unmilled parts. In the example, parts from an injection molding machine are to be milled before they are processed. But the parts are sometimes not milled. An idea is created to place two small blocks in a chute. The blocks allow a milled part to pass through, but will not allow an unmilled part to pass. This contact method is a great concept that can be applied in many different ways. The fixed value method can be used to control or warn an operator if something does not occur or something occurs too often. To put it simply, the fixed value can count the number of items, steps, or other numerically assigned elements and confirm or identify an abnormality. Let's look at an example of the fixed value method. In the assembly of a part with nuts and bolts, the exact number of nuts and bolts for the assembly is available to the worker. If any of the nuts or bolts are left over after the worker has assembled the part, A mistake is detected right away, and the worker can see numerically that he did not use the required number of nuts or bolts. Some other methods that can be used to detect errors with the fixed value method are with dispensers. A dispenser can feed the prescribed amount of an item into a bin. This is used quite often in the medical field. For example, when a pharmacy fills a prescription, a counter is oftentimes used to ensure that the right amount of the prescription is filled. Dispensers or counters can be used in both a control manner and a warning manner. Counters can be used to confirm the number of parts passed by, the number of process steps that have been completed, and they can help determine whether specifications have been met or not. For example, if a torque gun that automatically stops once a preset level of torque has been reached does not reach the required torque, you know there's an abnormality. There are many other ways that the fixed value method can be used. You may want to ponder the following question. Is there any process that I am part of where the fixed value method could be used? When you think of an answer, write it down and go and implement your improvement. To put it simply, the motion step method or sequence method determines whether or not only the appropriate steps of a process are completed. An example of this may be a form that is filled out on the internet. If the form is being filled out in the correct order, each step will allow you to pass to the next step. However, if it is not, it will prompt the user before you can move on and submit the information. Another very effective example that Dr. Shingo shares in his book, Zero Quality Control, Source Inspection, and the Poka-yoke Method, is the example of a device that feeds washers into the machine. The workers struggled with installation of washers and oftentimes omitted or doubled up on washers, which caused problems. In the book, Shingo describes a device that feeds washers onto a platform where they can be picked up and installed. If another washer is triggered before a washer is installed, it forces the washer onto a catch tray so that the operator can only install one washer. As you ponder these examples, consider this question. Is there a process that has a lot of errors or issues similar to the ones described in this example? Can I use a motion step method to warn me of an error or possibly to control a process? As you consider these questions, be sure to write your thoughts down when they come to your mind. You never know. Maybe you will find a process that you can error-proof using the Poka-yoke, motion step, or sequence method. Remember, these examples are meant to prompt innovative thinking, to get you to reflect on what you are doing and what could be done. The basis of all these examples is to prevent errors. With that being said, if your method is not exactly what you saw in this lecture, but it prevents an error, fantastic. Yeah! That is what it's supposed to do. Thanks for watching, everyone, and we look forward to seeing you in the next lecture.